Seventh question, modern physics, photoelectric effect. A very straightforward one that involves the Einstein's photoelectric equation. Now what does it say? The wavelength radiated has been decreased from 500 to 200, so the energy has been increased, and in doing so the K max becomes 3 times. We need to calculate the work function. Now the first thing is that this seems a bit hectic in calculation if you don't consider this fact. If you talk about the energy of light, that's hc by lambda. Let me consider in the case when it's 500 nanometer. So one way is that you plug in the value of h and c, or other way is memorize the product hc, and that is very close to 1240 electron volt nanometer divided by, you can go with 500, and that's nanometer. And you could see how easily you can calculate the value of energy in electron volt, isn't it? So use this idea while calculating the energy of the light. Now let's see, what does Einstein's equation say? The Einstein's equation says, let me call this as lambda 1, this as lambda 2 first to begin with. The value of kinetic energy is hc by lambda minus of work function, right? That's how it comes. So initially corresponding to lambda 1, this will be K max. And what has happened? On changing the wavelength to lambda 2, the K max has become 3 times, right? That's how it goes. So that's going to be 3 of hc by lambda 2 minus of work function. The work function would remain same because the metal is same. Now this is what you need to consider, and you have to solve, and when you solve that, phi, the value of work function, will be 0.61 electron volt. So option number 3, that's the correct one. Let's go to 8th question. The 8th question is a very straightforward formula based, and if you talk about calculation, cross product is involved. Now what is there? The charge is there which is in microcoulomb. Just be careful with that. And the velocity has been given. The external magnetic field, that has been given. And here we need to calculate the force on this charged particle. But while reporting the answer, just try to see that's F into 10 raised to the power minus 9. And that will obviously be easily done. F equals to Q V cross B. Now you could see here the charge is in microcoulomb and magnetic field 10 minus 3. So you would get 10 raised to the power minus 9. Bring that outside, and I believe you are well versed with the cross product. That's a straightforward one. Option number 4 will be the correct option. Let's go for 9th. The 9th question is something like this. This requires a good thought process. There is a cylinder and moment of inertia about an axis, perpendicular to the central axis is this much. That's a very known formula for a solid cylinder, isn't it? Now here the question is something different. You need to calculate the ratio L by R so that the value of moment of inertia would be as minimum as possible. But remember, there is a very important word, for a given mass. Now that is very much important. So you have a certain mass and you need to make a solid cylinder, but in different permutation combination, radius, length, they are different, and we need to search out that condition for which the moment of inertia would be minimum. All right. So here what I'll do is that starting with the expression of moment of inertia, that is equal to mr square by 4 plus ml square by 12. All right, that is there. Now the main job is that we need to see something, a condition we have to search related to R and L, of course. So what we'll do is that I will put the value of mass m as rho into pi r square multiplied by length. That will be a fair idea. So here starting with this, the value of moment of inertia now, that is going to be m by 4, that's a constant I can bring outside, and that's r square, and then L square by 3. Now, L square, I can do in this given way by 3, so that's m square by rho square pi square r raised to the power 4. That is what you get. I replaced the value of L from here, and there's L square. So this is what you get, the moment of inertia. Now we need to see the condition, that under what condition will the moment of inertia be minimum. So that's of course di by dr we are going to do, and we will equate that to 0, the condition of minima. So now that is going to give me m by 4, that's the coefficient outside, and this is 2r. And again, just have a look. The value of m is constant, so the derivative is going to give me minus of 4m square by 3 rho square pi square r raised to the power 5. That's the condition, and we need to equate this condition to 0. Is that fine? Now, how to come and involve with L? So back again, you need to put the value of m as rho pi r square L. So let's do that. Now we are left with a very little one. Let me continue this. This is going to be 2r equals to 4 by 3 rho square pi square r raised to the power 5. And what about mass? That's rho, so that will be rho square into pi square r raised to the power 4 into L square. This is what we get. Okay, and now this is going to give me something like this. Let's say the mutual cancellation, where it goes, rho square pi square. That gets cancelled there, and this will be 6 r raised to the power 6 by r raised to the power 4 is equal to L square, and 4 is of course here. So this is all done, and eventually, see, when you have lots of calculation at the end, dimensional consistency is really going to help us. Both sides we are correct dimensionally. And what will it give me? It's going to give me the value of r square by L square, as that's going to give me 2 by 3. So let's start hunting for the answer. I have to find L by r. So of course r square by L square is 2 by 3. So L by r will be root of 3 by 2. Option number 4, that is the correct one. Now let's go to the next one.